Look closely at this rock. To the untrained eye, it is just another stone, perhaps a pretty paperweight. But hidden within this unassuming form is light itself. This is silicon dioxide. This is quartz. And in the world of modern manufacturing, it is the beginning of one of the rarest and most precise transformations known to industry. The journey from a rough earth element to a flawless optical crystal. In a world driven by data, speed, and clarity, the components inside your devices cannot afford impurities. We are not just making glass here. We are engineering a medium for photons to travel with absolute precision. But before we can achieve that perfection, we must start at the source. Deep within the Earth's crust, we source the highest purity quartz. It is a geological lottery. Only a tiny fraction of the world's quartz contains the 99.99% purity required for this process. The moment this raw material arrives at the facility, the rare production begins. It is meticulously inspected, cleaned, and crushed. But this is not your grandfather's glass factory. There is no sand melting in a simple furnace here. This is a high-stakes operation where a single speck of dust can ruin a batch worth tens of thousands of dollars. We are about to strip this material of its natural memory and reform it into something that does not exist in nature. We are taking the chaotic earth and forcing it into geometric perfection. This is the preparation phase. Brutal, dirty, and absolutely necessary. Because to make something pure, you must first understand the impurity you are fighting against. The rock has been selected. The base has been set. But the real magic, the violent and scientific alchemy, happens next. This is the heart of the operation. What you are looking at is not fire in the traditional sense. It is controlled energy. We have moved beyond simply melting quartz. Here, in these custom-built furnaces, we are employing methods like flame fusion or hydrothermal synthesis. Imagine a room so hot that the very air feels heavy, yet so precisely calibrated that a temperature fluctuation of 1 degree could shatter a week's worth of work. Watch closely. See that tiny rod descending? That is the seed. In this chamber, powdered quartz is fed through a high-temperature flame. It melts, atom by atom, and lands on this seed. It sounds simple, but it is a ballet of physics. We are building a crystal, one molecular layer at a time. It grows at a rate of only a few millimeters per hour. Why? Because speed is the enemy of perfection. As the crystal grows, we are not just making a larger rock. We are aligning the optical axes. We are creating a homogeneous lattice structure that allows light to pass through without distortion, without stress. This is what makes it optical crystal rather than simple glass. The stress inside a material is invisible, but to a laser or a lens, it is a wall. Our job in this middle stage is to eliminate every internal wall, every bubble, every strain line. After days of relentless, automated precision, we extract the boule. To an outsider, it looks like a glowing, misshapen piece of rock. But to us, it is a diamond in the rough, quite literally. It is opaque, stressed, and hot. It has endured the violence of creation. Now, it must endure the patience of cooling. If we cool it too fast, it shatters. If we cool it too slow, we waste time. This annealing process locks in a clarity. We have created the blank canvas. But a block of crystal is useless. To make it an optic, we have to introduce it to something harder than itself. Precision. The chaos of the furnace is behind us. Now, we enter the silence of the finishing room. Here, the temperature is constant, the air is filtered, and the tolerance is measured in nanometers. We have our synthetic crystal boule. It looks like a chunk of glass, but it is actually a sleeping giant of optical potential. To wake it up, we must cut it. This is where rare production meets high precision. Using diamond-tipped tools and abrasive slurries, we begin the slow process of shaping. We are grinding the crystal down to within microns of its final dimensions. The sound is abrasive, but the result is smooth. Every scratch we put in now, we must take out later. It is a process of removal. We are subtracting everything that is not the perfect lens, the perfect prism, or the perfect window. After shaping comes polishing and testing. This machine is an interferometer. It shoots a laser through the crystal. The machine reads the light that bounces back. If the crystal is perfect, the light waves line up. If there is a distortion, the light waves are off. We are not just looking for scratches. We are looking for the very behavior of light itself. We are judging the soul of the crystal. This component might end up in a Mars rover, a deep-sea communication cable, or a surgical laser. Failure is not an option. From a dirty rock pulled from the ground, to a synthetic creation grown in fire, to a polished optical component that can split a single beam of light. This is the modern alchemy of rare production. It is a testament to human ingenuity. Our ability to take the raw earth and refine it into tools that extend our vision to the stars and into the microscopic world. This is Process Daily. Thanks for watching.